Up until the 1920s, everyone thought the universe...
Supernova explosions, the oxygen and other heavier elements began to disperse into space and spread out, helped by the force of the explosion and solar winds. When this spewed oxygen mixed or commingled with hydrogen and an energy source of some kind, perhaps heat from a nearby stellar explosion or lightning, yes, there can be lightning in space, hydrogen and oxygen, with the help of some energy, fused.
But was there anything before the Big Bang? We used to think that the theory of the universe could be divided into two parts. First, there were the laws like Maxwell's equations and general relativity that determine the evolution of the universe, given its state overall.
That has the effect over large distances of counteracting gravity and causing space to expand even faster. Spread over the vastness of the universe, it is the energy equivalent of only draws dark matter into diffuse halos. Within them, hydrogen gas forms clouds that become more and more dense over time. As gravity compresses the clouds, they begin to heat up, then finally ignite. Ultraviolet light from these stars begins to strip electrons from hydrogen atoms in a process called ionization. That causes surrounding regions to glow with visible light. The ionized gas appears as bubbles. They're associated with pockets of elevated temperatures, shown in red, as well as high concentrations of metals spread by supernovae, shown in green. The simulation reveals a dynamic that shaped the course of cosmic history. Heating from ionization tends to push the gas out. That suppresses the rate of star birth. Metals, on the other hand, allow pockets of gas to cool and fall inward. That cooling effect that enables this flow. Many of these early generation galaxies join in larger aggregations. Take the Spiderweb galaxy, 10.6 billion light-years away. A close examination shows that it sits in the middle of a cluster of galaxy fragments. This animated reconstruction, starting in the early years of the cosmic dawn, this simulation shows a slice of the universe in a region 350 million light-years across. The gravity of dark matter gradually concentrated visible matter into galaxy clusters. At the centers of large galaxies, black holes grew to supermassive proportions. As matter flowed in, they generated immense expanding bubbles of gas. 60 million years of its history. Within the disk, each flash of light is a supernova. As time goes by, thousands upon thousands of these explosions seed the galaxy with metals, the cosmic dust from which new generations of stars and solar systems are born.
Space at one time. And second, there was the question of the initial state of the universe. We have made good progress on the first part, and now have the knowledge of the laws of evolution in all but the most extreme conditions. But until recently, we have had little idea about the initial conditions for the universe. However, this division into laws of evolution and initial conditions depends on time and space being separate and distinct. Under extreme conditions, general relativity and quantum theory allow time to behave like another dimension of space. This removes the distinction between time and space, and means the laws of evolution can also determine the initial state. The universe can spontaneously create itself out of nothing. Moreover, we can calculate the probabilities that the universe is created in different states. These
explosions collected over time in one spot, the gravitational pull of all this matter began to coalesce and collapse into another generation of stars. The leftover dust from the star formation coalesced into planets, planetesimals, asteroids, and comets. So you would think that since water coalesced into planets, our planet would have all the water it has today from its very beginning. But it turns out
500 million years. So life appeared on Earth within 500 million years of it being possible, which is short compared to the 10 billion year lifetime of a planet of Earth type.
Years ago, it turns out that early asteroids had huge amounts of water too, since they had not been exposed to the heat of the sun for as long as they have now. The isotope ratios of near-Earth asteroids, wouldn't you know it, matches almost perfectly, and is a barren, lifeless, waterless ball of fire in the sky. There could not have been much water to start, so where did all this water come from? Join me as we go on a remarkable journey of one molecule of water from the time of creation to today.
But 4.5 billion years ago, when our planet was born, it was just a molten inferno. There was no place for any liquid water at all. Yet the ingredients needed to create water were there, locked away deep inside the Earth when the planet formed. As the first volcanoes erupted, one of the gases that billowed out was steam. And as the planet cooled, it formed clouds. It rained for thousands of years. As the first rivers formed, they began to fill up the lower-lying areas on our young planet, possibly creating the first oceans. But it's reckoned that even this relentless downpour only delivered around half the water that makes up our oceans today.
325 million trillion gallons of it.